Welcome to my presentation about optimistically compressed hash tables and strings in the USSR. This was the collaboration between me, Tim Gubner, and Victor Leis and Peter Bonds. This is mainly centered about hash tables. Hash tables are data structures frequently used in analytical queries, and it turns out they're pretty crucial for overall performance. There's certain problems because maybe you end up with huge hash tables and then access to those data structures is bottlenecked by main memory bandwidth. So we're basically hitting the main memory wall. And our question was, what can we do about it? In the literature, there's certain approaches to that. You can optimize access, doing some nice partitioning or prefetching. You could increase fill rate by using cuckoo hashing, Robin Hood hashing, whatever. Or you could shrink the table itself. This is what we try to explore. Basically, you can see here a little example. We start with a 100 megabyte hash table, and you can shrink it by 10x. With that, you can downsize your computer, use factor 10 less memory, which is probably cheaper for you and also nice for the planet, so Al Gore would like that. Or alternatively, you could increase query throughput by factor 10. Without having any disk spilling penalty. As a free bonus, this hash table would now fit also into last level cache, and hence you get an improved runtime. So basically you get higher throughput and free lunch, which is a better latency for hash table operations, which is pretty nice. And we try to explore that space. We propose three techniques. One would basically take the huge hash table and compress it into a smaller hash table. Technique two would make the used hash table effectively smaller by decomposing it into a hot and cold area. And technique three would handle strings, because it turns out strings are frequently used in real data sets. So first things first, we would try to compress a hash table. There are certain requirements that your compression needs to fulfill. It needs to be very lightweight, because hash table operations are very frequent and frequently the bottleneck too. So you don't have much cycles to spend on compression. However, in literature, there are different lightweight compression methods for scans that you might want to consider. However, many do not support very efficient random access, as you would need in hash table. And that's where our domain-guided prefix suppression comes into play. It's basically a variant of bit packing, which is itself very lightweight. And in addition to that, we also optimize the technique for efficient random access. So basically rows are independently compressed. However, for a one column, the compression stays the same, but you can decompress rows independently from each other, and each row is word aligned. So you don't need to do some initial bit shifting back and forth. And as an added bonus, you also get fast equality comparisons directly on compressed data, because you can basically transform them into the same compressed bit string. There are certain downsides to the compression. For example, you will have a hard time handling strings. Or alternatively, you can go even further than that. You can decrease the net effective memory footprint by decomposing the hash table into hot and cold areas. It's a very generic idea, and we explore part of that. Then you would end up with a hot and cold hash table. The hot hash table would contain frequently accessed data. The cold hash table would include the rarely accessed data. You would tune the hot hash table to be memory, cache resident. And in that hot hash table, you would put frequent strings, small aggregates. So if you have a sum in your hash table, it might be a very big data type or needs a lot of bits, just because you need to do a worst case assumption there, because cardinality estimates are not quite clear under a certain aggregate. However, as an observation, Subsums frequently fit smaller data types. So with that assumption, you could have a smaller bit string for example, a sum aggregate in the hot hash table, and after, say, a million iteration, write it out to the cold hash table. Or alternatively, or you can also store frequent strings in the hot hash table. What is not quite clear yet is what are frequent strings and how would you represent them in that hot hash table. This is where the USSR comes into play. In order to have frequent strings, you would assume many strings repeat. And to basically have an optimization for that, you would try to exploit dictionary compression somehow. But there are certain headaches with dictionary compression. You will see global dictionaries are pretty nice. As you would say, all strings are contained in a global dictionary. So in order to compare a string, you just compare a dictionary code. But once you get an update in there, you might have to rewrite the whole global dictionary and all places that use dictionary codes, which is quite a challenge. So you would stop the world and rewrite half of your database. It gets even worse if you have a cloud-based system or an MVP system, where actually workers have to update their own dictionary and then find consensus on a global dictionary across all workers somehow. On the other side, you would have per block dictionaries. So during a scan, you would scan a certain range of blocks. Each block can have its own compression. Say they're all dictionary compressed. However, each block has its own dictionary. And if you would actually want to use dictionary compression, you want to exploit dictionary compression during runtime, you would need to translate those dictionaries into global code somehow, in which you can do fast code comparisons instead of comparing the whole string, which you also have to pay a high price for. Or alternatively, you would not exploit dictionary compression for per block dictionaries and just decompress, as it's usually done. This is where the Unix string self-aligned region comes into play. It fits basically between global dictionaries, and per block dictionaries. It has the benefits of per block dictionaries, so you don't have the huge update challenges, but you can exploit dictionary compression there during runtime. The USSR is basically a query-wide dictionary, so if you start a query anew, you would build a new USSR with it. The USSR has a limited size, so it fits in cache. And you would assume it only holds frequent strings. And infrequent strings you would not even consider in that dictionary. There are certain technical aspects of the USSR implementation. For example, you can efficiently build it during a scan by exploiting dictionary compression. So if you scan a block that's dictionary compressed, you would basically insert the dictionary into the USSR. That gives you efficient insertion. And string pointers into the USSR are still valid C string pointers, which means it is very easy to retrofit into existing query engines. We basically implemented those techniques into vectorwise and run some benchmarks. First thing you see is basically, with our compression, you see a faster hash probe, especially for larger tables. So in this example, we see up to 2.7x faster hash probes for very large tables. For very small tables, you don't see much of that benefit, mainly because you don't have a lot of cache misses to begin with. You also see a little baseline benefit by using our compression, basically because 4 keys end up to be compressed into one word, and then you only check the one word in the actual hash table. But it's more an implementation thingy. What we also see is faster group bind strings. So suppose you have a string column consisting of 10 Unix strings, which are repeated quite often, and you do a group by on those 10 strings. you will end up with a table like this. For each string, for the strings, we vary the length. And you see in the table for each row, the first row speed up of the whole query. Second row, you see the speed up of the equality comparison, which is part of the whole query. And afterwards, the speed up of the hashing itself. We see for smaller strings, there is not much benefit. There is some benefit in terms of equality comparison, hash calculation. But however, there's not much of an overall speed up. On the other side, for very large strings, say strings with a length of 512 characters, we see a very huge speed up in equality comparisons. Basically, it says that many strings end up being in the USSR, and we can just use code comparisons there instead of doing the full string compare. We also see much faster hashing computation, basically because hashes are already materialized in the USSR, mainly because during the insertion, you would have to compute a hash, and you wouldn't want to throw away the already calculated hash. So we store it in the USSR, and doing hash computation, we can just retrieve it from there. And overall, those speedups accumulate to factor 22 for the whole query. We also see smaller hash tables in TBCH. So what you see here is the shrinking factor for our method with only compression in blue, and in orange with compression and our optimistic decomposition. What we see in both cases is maximal reduction of up to 4. So you can run 4 times the amount of queries in the same memory, basically. Or if you look in detail for compression alone, we see an average shrinking factor of 1.5. If we enable the optimistic splitting, we can push the average shrinking factor to 2.5, roughly. So turns out then you can run roughly 2.5 amount of queries without risking this spilling. We also tried a realistic workload. What we did for that is we looked into the Tableau BI data, which you can find online. We did it for one workbook. So we extracted the data set and we extracted queries. That workload has been discussed in 2 publications. One is the Get Real paper, which tells you this workload is basically string heavy. And we also published the whole workload. What we see here too is we have certain speedups for a lot of queries, up to factor 2.2 for the whole query, mainly because many strings are USSR resident. So we get fast string comparisons, fast string hashing, and so on. With the exception of, in our case here, query 6. What we see there is basically 0 speedup, so it runs in the same time. But we see not every string fits into USSR. We see this by looking at the rejection ratio. So 18% of strings get rejected. In which we also get a penalty for hash comparisons, for string comparisons, where we basically have to check if this string is part of the USSR and the other one is too. We can do an index a code comparison alone. So we get some branch misprediction penalty here too. However, there's not much damage done on the overall query. So no loss of performance there. So summarizingly, it can be said that we can make hash tables smaller and more efficient by using compression, optimistic splitting, so decomposing it into hot and cold, and our on-the-fly string dictionaries. This results in a faster runtime, less memory footprints, so you can basically have a higher query throughput. And what we didn't really mention that much in the presentation, our technique is easily composable with other hashing techniques. like cuckoo hashing or concise hash tables. So thank you very much for your attention. Questions?